This is video 2 of 13 of heat transfer. In this short video, I will explain how to derive the fundamental equation of heat conduction. We can't solve the equation, but let's then first derive the equation, because I said we need boundary conditions and various ways of getting solutions. So if we then look at our heat transfer problem again here, we're now talking about fire giving heat to the structure and then heat transfers within the structure by conduction. We're trying to find out then how conduction happens. Of course, we have our law of Fourier's heat transfer. So we have Fourier's law of heat transfer, which relates heat to temperature gradient. We're trying to find out temperature distributions within the structure. That's what we're looking for. So there's no point, was not very good to have a heat in here because we don't really know. So we then have to find a way of them removing heat, or removing this term of heat and replacing that by temperatures. So that's then our starting point, but as I said, we want to then remove or eliminate this heat in here and replace it by temperatures. Whereas our starting point, again, as I said before, our starting point is always the principle of heat conservation or energy conservation or heat balance. That means then net heat into any body, into any system, which means heat input minus heat output, is the same as the amount of heat needed to raise the body temperature. So that is then our heat conservation. Simply net heat into the system equals to the heat that is used to raise the body temperature. So if we then take a infinitesimally small area, block of volume from our structure, okay, and then we have, say, in one direction, in the x direction here, just for now, in the x direction here, because in the y and the z directions, then we have the same thing, or similar things. Let's just then derive the equation in the x direction, or part of the equation in the x direction. On this left-hand side, we have heat going into, so assume heat goes in that direction. We have heat going into the body. On the right-hand side, we have heat going out of the body. Now in this case in here, we don't have steady state heat transfer anymore, meaning then the heat going inside the body on left-hand side, and the heat going out of the body from on the right-hand side, they're not equal anymore. So the difference then means there is some heat accumulation or heat outflow, depending on whether one is bigger than the other. There is some heat accumulation or heat storage into the system. I'm trying to find that out. Okay, so that's then trying to find out how much heat, net heat, goes into the body from the x direction. So that's what I was trying to do. So we then afterwards then we can add in the z direction, in the y direction, z direction together to give the total. Let's just now look at what's going on in the x direction. So on the left-hand side, okay, on the left-hand side, we have heat transfer by conduction. Okay, this is only one part of the whole body. Okay, heat transfer by conduction. Our Fourier's law of heat conduction has defined this: the amount of heat by conduction per unit area in this direction. Okay, as temperature gradient in the x direction times thermal conductivity in the x direction. Thermal conductivity might change in different directions. For now, let's say we're dealing with x direction. So that's then heat going into the body from the left-hand side per unit area. We simply then multiply this by the area of this little block, which is, of course, y and z, because that's perpendicular to the x direction. So that's then how much heat flowing into the body. okay, flowing into the body, because in this direction is flowing into the body from the left hand side. Let's then say how much then goes out of the body from the right hand side, which is now this term. Of course, now this term is simply then linked to the left hand side, but changing the temperature. So on the left hand side, we have this. On the right hand side, we have a very similar equation, but our temperature is not the temperature on the left hand side, but the temperature on the right hand side. So we have the thermal conductivity on the right hand side, that's heat on the right hand side, but its output is going out, okay, is out of the body. Thermal conductivity of that position, but the temperature in here now is the temperature on the right hand side, on this side, which of course is then the temperature on the left hand side plus a bit of increment of temperature. Okay, so that's then the temperature on the right hand side, and then this is then the temperature gradient on the right hand side. Of course, temperature gradient times thermal conductivity at this position. Of course, remember there is also this minus sign in here to indicate flow of heat in the opposite direction of temperature gradient. So that's then our basic Fourier's law of heat conduction, but applied to the right hand side, which in this case then is heat outflow. And then again, then we multiply by the area across the heat flow, because the heat flow from Fourier's law is per unit area. So in the end, then we have the amount of heat going out from the right hand side equaling that. So one is in, on the left hand side is inflow, on the right hand side is outflow. So on the left hand side is inflow, on the outflow in there. If we then one minus the other, on the left hand side inflow, right hand side outflow. So one minus the other gives us the net heat into the body from the x direction. If you then use the previous two slides, you will then find then the total net is this much. Okay, it's simply thermal conductivity of that position. Now, in the previous equation, we have thermal conductivity on the left hand side and thermal conductivity on the right hand side. If then, on the other hand, if the area is very small, the little body in here is tiny, then the thermal conductivity we say then does not change with position. That suggests then use thermal conductivity in the x direction, and then that of course multiplying together gave us the volume of this little block. So that's then in the end the amount of heat coming to the body, net heat going into the body in the x direction. In the y direction, then we simply change x to y. In the z direction, we change x to z. So in the total, then we have the amount of heat going into the body in the three directions, x, y, and z. And of course, then in the previous equation, we have multiplied by the volume of this block. The volume is simply dx, dy, dz multiplied. So that's then the amount of heat going into this body. As we said before in the previous lecture, the amount of heat in this case going into the body then is used to increase temperature of the body. So increase temperature of the body, the amount of energy used, as I said before, is then the temperature increase times volume and density, which gives us the mass. So density times volume gives us the amount of mass of this volume times specific heat, because specific heat is energy per degree temperature per unit mass. So if we then multiply the total mass and then multiply the total temperature, that then gives us total energy. But of course, energy is not the same as heat. On this side is heat. Heat is the change of energy rate. So then we then divide the energy here, which is because of this temperature increase, by time. Okay, that's then the heat in the end. So on the left hand side, if we then write the whole equation of heat, we have volume on the right hand side. If we then write the whole equation, then we'll also have volume in here. So in this equation, the end, then we delete or cancel out the volume, and then we become this big equation, which is this then the fundamental equation of heat transfer, everything expressed in terms of temperature inside the body. Of course, we can't solve this equation because, as I said before, we don't have the boundary conditions, or we need boundary conditions to solve this equation. So at least then we know which equation we want to solve, even though it is very difficult to solve, and even though we need boundary conditions. So that's then the end or summary of this short introduction to heat conduction. This is all we're going to be learning about heat conduction. So we started with Fourier's law of heat conduction, and then we're trying to eliminate this heat in here in this equation, because we're only interested because we can only find solutions if of temperatures if we then relate everything to temperatures through a process of heat balance or energy conservation, and we found out how much heat or energy, how much heat stays inside the body in the x direction, in the y direction, in the z direction per unit volume. Okay, per unit volume, and then the total together then is used to increase the temperature of the volume at this rate of temperature increase. So this then is the final equation of heat conduction. As I said, it is complicated, it is difficult to solve, and we need boundary conditions to solve that, but at least we know what this equation is and where it comes from.